Next, we're going to be talking about alcohols, and we're going to do two different parts. The first part is going to be discussing the structure of alcohols and the synthesis of alcohols. In other words, how do you prepare them? And an alcohol is an organic molecule that contains an OH functional group, and because oxygen is so electronegative, it pulls a lot of electron density toward itself, especially away from this tiny little hydrogen. So what we end up with is a huge partial minus and partial plus on these two atoms. And so the OH group is a very, very polar functional group, and that's going to define a lot of its physical properties. They can undergo hydrogen bonding with each other. So in other words, one molecule of an alcohol with a big partial minus, partial plus, can interact with another molecule of alcohol, partial minus, partial plus. And there's such a strong attraction between the oxygen on one and the hydrogen on the other that we actually draw a dashed line connecting them. We call that a hydrogen bond. And it's easy for the protons to be transferred from one structure to the other, and it results in a very strong association, a very strong affinity for one molecule of an alcohol to another molecule of an alcohol. The physical property effects we see on that is that we see an increased boiling point, because if these are very strongly attracted to one another, it's going to be difficult to tear them apart from one another and put them in the vapor phase. Okay, we also see an increased water solubility, because very much like water, like dissolves like, water is polar, water can hydrogen bond, so very strong affinity between alcohols and water. Another feature that we're going to be seeing is that the OH group is acidic. In other words, it can be deprotonated. It can act as an acid. It can donate an H plus very easily, and so we'll see reactions of alcohols with a wide variety of bases as well. Let's take a look at some sample boiling points. These boiling points are listed in degrees C so that we can observe the effects on boiling point by various functional groups. If we take a look at a molecule like pentane, okay, completely non-polar molecule. All it has are carbon-carbon bonds, carbon and carbon-hydrogen bonds, all very non-polar. And we compare that to an ether, let's say, where we have an oxygen in here, okay, which now makes it, we have some polar bonds, and so there's a small dipole moment here. This is a polar molecule, but you don't see a huge difference in boiling points. These are about the same molecular weight, and not a huge difference. They're essentially the same. So the polarity isn't having, this small amount of polarity is not having a big difference in the boiling point. But instead, if you have an OH group for that oxygen, rather than just an oxygen with carbons on either sides, now look at the huge jump we get in boiling point difference. And even ethanol is now a smaller molecule, yet it has over twice the boiling point. So this effect here is because of hydrogen bonding, and those ethanol molecules are very strongly attracted to one another, and so it's difficult to take them apart and put them into the vapor phase. So you have to put more and more energy into it, and that increases the boiling point. Okay, when we compare ethanol to butanol, how do we explain that difference in boiling points? They both have the OH, so they have the same polarity, same hydrogen bonding capability, but now we see the trend where as you increase the molecular weight, you increase the boiling point. So just a larger molecule, all other things being equal, a larger molecule is going to have a higher boiling point. And then finally, I put this molecule on here. This is called ethylene glycol. He's an example of a diol with two OH groups. Oh, in fact, I just noticed a typo with my structure here. Excuse me. Ethylene glycol has just two carbons and two OHs. And notice this boiling point, 197. So lots of hydrogen bonding in the case of ethylene glycol because it has two OH groups. So a very big network of hydrogen bonding there. That high boiling point is very useful to us. We use ethylene glycol as a component of antifreeze. And it's good in that capacity because it has it's very hard to boil, and antifreeze, the coolant that goes through your car and cools down the engine, needs to be very high boiling because it's going to get very hot. We don't want it to just boil away. You can't just fill your radiator with water because the boiling point is too low. So we can see here a clear trend that the presence of an alcohol, of an OH group or multiple OH groups, is going to have an increase in the boiling point of those molecules. When we take a look at water solubility, we describe water solubility in terms of grams per 100 milliliters of water. So if I had a 100 milliliter sample of water, how much of this material could I dissolve in there? And if we take, again, a look at something like pentane, this liquid is completely immiscible with water. They form two separate layers. There's no solubility, and once again, it's because this is a completely nonpolar molecule, and so it has no affinity for water. In fact, you could describe this as being hydrophobic. Something that is nonpolar is hydrophobic. It fears water. There's nothing about it that's similar to water. Remember, we're talking with solubility. We're always talking about like dissolves like. The more similar a molecule is to water, the more it has in common with it, the better the solubility. Okay, and so for example, if you put in an ether, now you have a little bit of polarity, and we have a big jump in water solubility. This does have appreciable water solubility, and that's because it can accept hydrogen bonds from water. So in other words, this oxygen can be attracted to a water molecule and form some hydrogen bonding there. So it can be a hydrogen bond acceptor from water. So even though this ether can't hydrogen bond with itself, if you just had a sample of ether, it can undergo hydrogen bonding with water, so that increases its water solubility. This is diethyl ether because it has some water solubility. That's why whenever we use ether in a reaction workup and we're doing an extractive workup, the ether layer is wet with dissolved water, and it must be dried. So any extractive workup that you do, where you partition your reaction components between an organic layer and an aqueous layer in a SEP funnel, for example, if you're using ether, ether has some water will always dissolve into the ether layer and the ether going into the water layer. And so part of any workup procedure is going to be taking that ether layer and drying it somehow, removing that water by using a drying agent like calcium chloride or magnesium sulfate, and getting rid of that water. And by looking at the structure, we can see the polarity and the hydrogen bonding capability that would explain why it does have some water solubility. And it's also going to be something that's very relevant to us in the laboratory. Okay, but then when we move to a molecule in OH, you might think, well, now there must be a huge jump in water solubility because now we can both donate and accept hydrogen bonding, a lot more interaction. But when we look at these two molecules, they both have 4 carbons, but this has a really long carbon chain that's nonpolar. So we end up getting this balance, this trade-off between this nonpolar part and this polar part, this hydrophilic part and this hydrophobic part. And so you can see that actually these have very similar water solubilities, not very different at all. Okay. However, if you shorten up that nonpolar chain and you look at something like this is ethanol. It's completely miscible with water. So now it's a polar enough molecule, and it has this hydrogen bonding capability that it's soluble in all proportions. You can never have too much ethanol so that it separates out as a separate layer from water. This is the alcohol. We're studying alcohols in this unit, and we've heard of alcohols before in our day-to-day lives. One of the alcohols is one that humans can drink without getting too sick, and that's grain alcohol. And this is the actual alcohol structure. You know, as an organic chemist, our definition of alcohols extend to anything containing an OH group, but in our everyday lives, this is the alcohol that's referred to as alcohol that's drinkable, and it's the 2-carbon chain called ethanol. And of course, the alcoholic beverages that are out there are aqueous solutions with some alcohol in there, right? The proof tells you what percentage of alcohol is in there, and the rest of it is just water. So this is something that we might already have seen some evidence for, that ethanol is in fact miscible with water. Okay, let's talk about the other physical property, the other reactivity or feature of an alcohol, and that is the fact that it's acidic. It can be deprotonated. And so we have, let's compare an alcohol, OH, to an amine, NH, and see if we can maybe explain why an OH is pretty acidic. In fact, if you look at their pKa numbers, This is a pK of about 16. That's a very low number, really easy to deprotonate an alcohol, where an amine has a pK of about 40. So let's just do this comparison as a review of things that affect acidity and basicity, and see if we can explain that and understand why alcohols are so easily deprotonated. Okay, as usual, we're going to want to consider the conjugate base of each of these to decide why they have such a big difference in pKa. So, in other words, let's let methanol be an alcohol, be an acid, and get deprotonated. So instead of having an OH, we'll have an O-. That's the conjugate base of methanol. The conjugate base of methylamine has an NH with a minus. So we remove an H plus from each, and now we compare the two. We have an O- versus an N-. And which of those is more stable? We look for a difference in the stability of the conjugate bases to explain differences in acidity. Okay, well, we know that oxygen is more electronegative than nitrogen, so let's start by stating our facts. Oxygen is more electronegative than nitrogen. Okay, so if you have a negative charge, would that prefer to be on the more electronegative atom or the less electronegative atom? It prefers on the more electronegative. So oxygen better handles the negative charge because it is more electronegative. O- is better than N-. Okay, so that means CH3O- is the more stable and therefore less reactive. If you're more stable, you're less reactive, and therefore weaker conjugate base. Whichever conjugate base is more stable, that makes it less reactive, that makes it the weaker conjugate base. And the weaker conjugate base has the stronger parent acid. So that can be our last comment. CH3O- has the stronger parent acid. And is that what our pKa data tell us? Sure. Again, pKa of 16, that's a difference of 24 units. That's cajillions times more acidic having an hydrogen on oxygen compared to a hydrogen on something like a nitrogen. Okay, so it's because oxygen is so electronegative. If you think about the periodic table, we all know that fluorine is the most electronegative atom. Oxygen right next door is the second most electronegative atom in the periodic table. So oxygen, that means it's really good at pulling electron density toward itself, and it's very, very happy having a negative charge on itself. So, so that means it's pretty reasonable to deprotonate an OH and convert it to an O- because oxygen doesn't mind having a negative charge. Okay, so if we wanted to deprotonate an OH to give an RO-, these are called alkoxides, and because we have an alkyl group and an O-. So just like hydroxide is HO-, alkoxide is RO-. How would we prepare an alkoxide if we wanted to? Well, what we'd have to do is we'd start with the alcohol, and we would completely deprotonate it. We want to remove 100% of the H plus from all the OH molecules, the OH containing molecules. Okay, and there's going to be two strategies we can have for this. One option is we can use a very strong base, like sodium hydride. Now again, when I say strong base, what do you think of sometimes as strong base? You think hydroxide, NaOH. NaOH is not going to do it. And think about it. You can't use an O- to create another O- and be able to do so in an equilibrium that's going to be heavily favored in one direction or the other. This would simply set up an equilibrium with water and the alkoxide. And we don't want an equilibrium, we want a one-way street. So rather than using NaOH, the base we're going to be using is sodium hydride, that's NaH. So that's sodium plus and H minus. H minus is called hydride. And this is a very effective base. We just said the alcohol can act as an acid. So what happens when you react these two? The base is going to grab that proton, leave the two electrons behind on the oxygen. So it's going to give us an O-. It's going to form methoxide here. If we use sodium hydride, we're going to get the sodium salt. Okay, so this forms sodium methoxide, just a little vocabulary in there on how we're going to name our alkoxides if we have them. And what's the other product in this case? When we use sodium hydride as a base, we have an H minus. It's combining with an H plus. So our other product is hydrogen. What do you know about hydrogen? It is a gas. It is going to bubble away. So tell me, how does this reverse reaction look? If you wanted to consider, whether or not it's going to be going forwards or backwards, well, because our hydrogen gas, our product, one of our products is leaving, the reverse reaction becomes impossible. Okay, so there's no reverse reaction. So that's what makes sodium hydride something that's ideal for making alkoxide. 100% of the alcohol will be converted to an alkoxide. Another possibility is to use a redox reaction to do this, pretty much the same transformation. But instead of using sodium hydride, we're going to use sodium metal. So this is sodium 0 or sodium dot. This is a metal. It has a single electron in its valence shell that makes it a very good reducing agent. We've seen sodium metal as a reducing agent for alkynes, doing the dissolving metal reduction to a transalkene. Okay, if we were to react with an alcohol instead, what happens is we end up forming two equivalents of sodium methoxide and hydrogen gas. We actually get the exact same products out that we did in this acid-base reaction, but this mechanism is more complicated. It's not a simple proton transfer. It's an electron transfer. So we call those redox reactions. And we look at this reaction carefully. We see that we're starting with sodium metal, and we end up with sodium plus. So that is the oxidation that's occurring. In other words, sodium is releasing that electron, donating it to someone else, getting oxidized itself, and causing a reduction in the hydrogen of the methanol. That started out with a +1 oxidation state, but when it's in its elemental form as hydrogen gas, it has a 0 oxidation state. 0 oxidation number. So we went from a +1 to a 0, that is a reduction in oxidation number, that is a reduction, a gain of electrons. So this mechanism is not one we're going to study. It's more of a, predict the product or providing the reagents. If you want to completely, actually the other thing, like all redox reactions, this reversible reaction is impossible. Redox reactions always go to transfer the electrons to give a more stable species. So what's great about both of these is that they are both irreversible. And so if we need to form an alkoxide, you have two good choices, sodium hydride or sodium metal. Those are two great reagents that we can count on. Now, sodium metal works, but sodium, lithium, potassium, those are all group 1A, and those would all work well to do this oxidation. As you move down in the periodic table, your atoms are getting bigger and bigger and bigger, so that electron is being held even further and further from the nucleus. That makes it a lot more reactive. So something like potassium, which is bigger, is going to be more reactive. And so that's useful for certain alcohols like this T-butyl alcohol. This is a weaker acid than something like ethanol or methanol. And why is that? Well, because these alkyl groups, this tertiary alcohol, this is a tertiary alcohol. Those are in general weaker acids than and less willing to give up a proton than a primary or secondary, because these alkyl groups are all electron donating, so that's not a good thing. If you want to be forming an O- here, that would be destabilized by those those alkyl groups donating electron density. So this would be a very, very, very slow reaction if we use sodium metal or even lithium metal, but if you use potassium metal, that's going to be strong enough to do this redox reaction. And same idea, our products are going to be an O- K+. We're going to get the alkoxide, and the other product here is this H+ that we have is going to come off as hydrogen gas. Okay? When we balance our redox reaction, you see we're using 2 equivalents of the alcohol and 2 equivalents of the potassium, so we'll get 2 equivalents of this guy. This is called potassium T-butoxide, or TBUOK. We've seen this before as a nice, strong, bulky base that we've used, and the reason that we usually see this as the potassium salt is because that's the one that's commercially available. That's the one that's typically made. That's how we typically make it, is by using potassium metal to do this redox reaction. And one other example of an alcohol, when we're talking about acidity, let's talk a second about phenols. A phenol is a very special alcohol. It's when we have the OH group on a benzene ring. And these are significantly more acidic than other alcohols. So where an ordinary alcohol has a pK of something like 16 or 18 or somewhere in that range, a phenol has a pK of about 10. So again, what, 8 zeros, that's tens of millions of times more acidic. And so in that case, this is NaOH is okay. This is a weaker base is okay. You don't need to use sodium hydride. You don't need to use sodium metal. You can, but you don't have to. And typically, we try and use the least reactive base we can because that's going to be easier to handle and you know, maybe cheaper or a simpler reaction to run. Okay, so weaker base is okay. And when we do the deprotonation here, so now we're using hydroxide to do our deprotonation. The products then are going to be sodium phenoxide, is what we call it when we have a phenyl O-, sodium phenoxide, and water as our other product. Now water has a pK of about 16, which would not be good if we were trying to deprotonate something with a very similar pK, but because this is so much more acidic, it's a million times more acidic, we know the direction lies, the equilibrium lies in the direction of the weaker acid-base pair. So in this case, the equilibrium would be very much favored in the forward direction. So in fact, hydroxide is very effective and is suitable for deprotonating a phenoxide and essentially completely converting it to the anion, to the O-, the alkoxide. Now, how would we make an alcohol group? Where does an OH group come from in a structure? And there's a few different strategies we can have for this. One way of installing that OH group is by doing some kind of substitution reaction. In other words, if I had a leaving group on the carbon chain, I could replace that leaving group with an OH, and then my resulting product would be an alcohol. So we have a few different substitution mechanisms. We have SN1 mechanism, we have SN2 mechanism. Let's take a look at both of those. If we wanted to do an SN2, remember SN2 is backside attack, so we need a strong nucleophile to come in and attack and kick off the leaving group in a single step. So the nucleophile we would use here would be hydroxide, very strong nucleophile, so it's great at doing the SN2. The problem is that it's also a very strong base. And so we have a competition going on between the SN2 that it would do if it was a nucleophile, or an E2 is another thing it could do as a base. It can go after a proton. So the way we decided between SN2 and E2 this competition is we considered steric hindrance, knowing that the backside attack can't have any steric hindrance. And so when would the SN2 mechanism be reasonable for alcohol synthesis? Only when our carbon chain has very little, if any, steric hindrance. So if we have a methyl halide, or if we have a primary halide, those would be best. Maybe it's allylic or benzylic, that would also help support the SN2 mechanism. Okay, so for example, if you had ethyl bromide and you treat it with sodium hydroxide, because this is a primary RX, a primary alkyl halide, this is our electrophile, the hydroxide is our nucleophile, no problem attacking the carbon, kicking off the leaving group. This would be a great SN2. This would be a great SN2, and this would be a reasonable way to make an alcohol. We just made an alcohol by using hydroxide as a nucleophile. Okay, this one is a little trickier because we have, if we look at this carbon, it's now secondary, so it has some steric hindrance. But because it is allylic, this is something that makes the SN2 not so bad, and so that's something that would make this possible. And the reason SN2 is okay here is because the pi bond stabilizes the transition state of the SN2. So we have p orbitals here, and we form a p orbital as the nucleophile is kicking out the leaving group, and so that helps make the SN2 a faster reaction, so it competes better. So this is another case where even though it's secondary, you would probably get as your major product the substitution product. Okay, but that's a rare case if it's benzylic, meaning it's next to a benzene ring, or allylic, meaning it's next to another double bond. Otherwise, if you're a secondary alkyl halide, your secondary leaving group, there's enough steric hindrance where SN2 is not going to be favorable. Okay, so for example, if we just have plain old cyclopentyl bromide and we try to do hydroxide, there's enough sterics here that instead of doing the SN2, the E2 is faster, meaning it acts as a base. It attacks the beta hydrogen, that's what bases do, forms a pi bond, kicks out the leaving group. So the E2 elimination competes with the SN2 anytime our nucleophile can be a strong base. And because we're using hydroxide in this case, for sure that competition is going to be there. Okay, so E2 is favored in that case, and of course if it's tertiary, there's no chance of having the SN2, so that's favored as well. And remember, if you have a phenyl or a vinyl alkyl halide, we can't do our SN2 mechanism there. So, because he is on an sp2 hybridized carbon, a leaving group on an sp2 hybridized carbon is not what we have for backside attack. Backside attack, we need a tetrahedral carbon. We need an sp3 hybridized carbon. So it's a reaction of alkyl halides. Not vinyl halides, not aryl halides. So this would be no reaction. Okay, so SN2 is one option for doing a substitution synthesizing an alcohol. We could also do an SN1 reaction with water as our nucleophile. Now this is a weaker nucleophile, so water is not going to come and attack and do a one-step mechanism, but we can get a substitution via an SN1 mechanism where we have a carbocation involved. We call this reaction solvolysis because it's reacting with a solvent, or more specifically hydrolysis, since it's reacting with water. Okay, and what we need in this mechanism is, because we are forming a carbocation, this is going to be a reasonable option only if a favorable carbocation could be formed. So for example, if you have an allylic leaving group or benzylic or tertiary, those are all excellent carbocations, and so those would all be decent SN1 mechanisms. So for example, that we have this benzylic carbon with a leaving group. Water is a weak nucleophile, so that's why we are deciding that it cannot be the SN2, it has to be the SN1. And what mechanism is that? What does that mean? That means because there's no one here to attack, the leaving group just leaves on its own to give a carbocation. And to this electrophile, we have water react as a nucleophile. To give an OH2, and then we can deprotonate to get rid of that O plus. You could use the Br minus here to kind of tidy up. You might see that sometimes, but really water, because we're doing hydrolysis, water is our solvent. Water we have a lot of, so that's probably going to be our best base here. And we're going to get the alcohol. Now tell me about the stereochemistry here. What is the stereochemistry of this CO bond? Because the carbocation is planar, when water attacks, it can attack from the top face, it can attack from the bottom face. Both of those are going to be equally likely. So what we're going to get is a mixture of having the OH as a wedge and an OH as a dash. So SN1 is not a good situation with a chiral center unless you it's okay to have a racemic mixture, then SN1 is good. But if you want stereo control, then you need to find something like an SN2 where you can do that backside attack. Okay, so here we get racemic mixture. The other thing to keep in mind with water and trying to do an SN1 mechanism is that because you have a carbocation in your mechanism, it can rearrange. So if it is not one of these very, very stable carbocations, like in this case, we would get a positive charge here. And so we might think that we could, when we do hydrolysis of this, we might get an OH in this position. Okay, but in fact we don't, because we're right next to a more substituted carbon, and if the carbocation could somehow get over there, then it would be a more stable carbocation. So that in fact is the major product we get. With rearrangement, we get this substituted product. So we always have to keep that in mind anytime we want invoke a mechanism involving the carbocation, we have to make sure that if there's a possibility of rearrangement, we account for that, and that needs to be the product that we're expecting. Okay, this is a good mechanism for you to try. See if you can do that complete SN1 mechanism involving the carbocation rearrangement. Okay, another reaction we've seen in the past that gives an alcohol product is starting with an alkene starting material. And if you add water across an alkene double bond, you'll end up with an alcohol product. And for hydration, remember we saw 3 different methods for adding water across a pi bond. If we used either H3O plus or this one, oxymercuration reduction or oxymercuration demercuration, this was the case where we broke the pi bond, we add an H and an OH, and where did the hydrogen go? It's going to follow, both of these follow Markovnikov's rule, meaning the carbon with the hydrogen over here gets the hydrogen. And this last method, hydroboration oxidation, this 2-step method, does the opposite regiochemistry. We break the pi bond and we add an H to the more substituted carbon and OH to the less substituted carbon. We add the hydrogen to the carbon without the hydrogens, and we have our CH3 there. Okay, so our regiochemistry is different here. How about the stereochemistry? Is there anything we knew about the stereochemistry here? With the hydroboration, you remember that mechanism? Hydroboration, both the boron and hydrogen are added at the same time, which means they have to add to the same face. So another result of this is also we get syn addition. So that means we need to show the H and the OH coming from the same face. For example, they could be both wedges, which forces this methyl group to be a dash. Okay, of course, it can come from the opposite face. It can come underneath, and then we would get the enantiomer, in which the H and the OH are the dashes and the methyl group is the wedge. Okay, so when we take a look at these products, we see that this is an alcohol product that we get. So another way that we can maybe put in an OH group on a carbon chain is to start with a double bond, and then we could put the OH maybe on one carbon or the other depending on the reaction conditions we use, the reagents we use. Okay, we could also do an oxidation reaction of an alkene. That would give a diol. So for example, KMNO4, or if we use OSO4, this was one of the several oxidations we studied for alkenes. And this is the one that broke the pi bond and did a dihydroxylation. It added 2 OH groups and it added them to the same face. So again, we would show some stereochemistry here, OH up, which then forces this methyl group down. And we call that syn dihydroxylation. And if it came from the bottom face, that would be the enantiomer. So this makes a special kind of alcohol, right? This makes a diol, where we have 2 OH groups, one right next to each other. So if we have that special kind of target molecule, we can consider doing a dihydroxylation of an alkene. Okay, and another great way to make an alcohol is to start from a ketone or an aldehyde. So in other words, if I had a carbonyl on my carbon chain, that could get converted to an alcohol group. Okay, and the way we do this is we react it with a nucleophile of some kind. Because an aldehyde or a ketone, we're going to be studying these later, and we'll see that these are electrophiles. They're electrophiles because this carbon-oxygen bond, of course, is polar because oxygen is electronegative. It's also very polar because this has resonance. That has a resonance form with an O- and a C+. So as a result, the carbonyl carbon is very, remember this is called a carbonyl. I'm going to be using that word a lot. That means a CO double bond. That's a good word to know. A carbonyl has the following polarity of partial positive on the carbonyl carbon, partial negative on the carbonyl oxygen. That makes this carbonyl carbon a very good electrophile. So if you were to react with a nucleophile, what happens is it attacks the carbon and it breaks this pi bond and puts those electrons up onto the oxygen. And we get some kind of intermediate like this. Okay, if we were to then treat this with H3O plus, let's say, some kind of workup procedure at the end of the reaction, we're going to provide it with some kind of acid, some kind of proton source. What will happen is we can protonate that O- with our work up and convert it to an OH group. So when we have a nucleophile adding into a carbonyl, the product we get has a nucleophile now connected to the carbonyl carbon and an OH group where the carbonyl oxygen used to be, or the CO double bond used to be. Okay, and so our product here is an alcohol. So this is another very good way to synthesize an alcohol and to come up with an OH as part of our final structure. So what nucleophile do we have available to us? Well, there's several we can look at. One nucleophile we've already seen is this acetylide ion. He would be a very good nucleophile. We saw him doing SN2s with alkyl halides, but he would also like to add into a carbon. He'd be good at that. Okay, but there are some other nucleophiles that we'll be studying this unit that we have not yet seen. This one is called a Grignard. It has an R group. That means some kind of carbon chain with a magnesium and a halide. And hydride, an example of that is something like LiAlH4. So we're going to look at these new reagents and see, learn something more about their reactivities and what they do. Here we see a C-, so I can see how that's going to be a good nucleophile. Okay, but what about RMGX? How do we get a nucleophile out of that? Well, this magnesium has a +2, and the chloride, if you think about their oxidation state, the chloride has a -1. So that gives the alkyl group, this carbon group, the character of being a carbanion, being an R-. So we're going to be looking at things like this Grignard reagent as a source of R-. That would be a very good nucleophile. Okay, and hydride, as given as an example with this reagent, hydride means we have an H with a lone pair and a negative charge. And that would also be a very good nucleophile. So we're going to be adding, maybe an alkyne group here, or an R group here, or a hydrogen here to be this final group in the position of where the carbonyl used to be. Okay, so let's talk about this RMGX. It's an example of what's known as an organometallic reagent, and it's called that because it has both an organic part and a metal. So M just kind of represents some sort of metal. And R group, as usually, is some organic component, some carbon chain. And these are called organometallic reagents, and we're going to see two examples of them. One is called RMGX, it has the formula of RMGX. One is RLI. And the first thing that we'll do is we'll talk about how to prepare them. Where do they come from? Okay, and they're going to be prepared from an alkyl halide, or a carbon chain with a halogen on it. So for example, if we were to take methyl bromide or bromomethane and react with magnesium metal, and here you're literally taking shavings of magnesium metal, magnesium turnings, tossing them into your reaction, stirring that reaction, heating it, you will see your magnesium metal dissolve as it reacts. And what it does is it inserts itself into the carbon-bromine bond. So this is not a mechanism that we're going to worry about, okay, but we want to know what the product looks like, and that's where we insert a magnesium into the carbon-bromine bond. The other product here is going to be, some salts. We're going to lose the bromide. We're going to make magnesium. That's not too important. Okay. Now, what we just said about this guy, he's called a Grignard reagent, by the way, named after the chemist who developed the reagent, and it has the general formula of RMGX. So this R in this case is just a methyl group. We'll see it could be just about anything. The X is very often a bromide, but it also could be a chloride or an iodide. You can have another halogen there as well. And as we just mentioned, since the magnesium has a +2 and the bromine has a -1 as their oxidation state, and the Grignard is a neutral molecule, that means the carbon has a -1 oxidation state. And these are not ionic compounds, so you can kind of think of this as having a combined partial +1, and this has a partial -1. If you want to think of it as a partial charge rather than a full ionic charge, either one of those ways to consider it would be good. And so because it's a carbon with a negative charge, that means he would be a very good nucleophile. And what's interesting is we just came from methyl bromide. Now what kind of reactivity does methyl bromide have? Here we have -1 for the bromine, so we had a partial positive for this carbon. We went from an electrophilic carbon, and then by attaching a metal to it, we turn it into a nucleophilic carbon. So that's what organometallic reagents look like, and that's how they behave. Is that any carbon bearing a metal has negative charge character, anionic character. Okay, so the Grignard is one option. We get that when we react an alkyl halide with a magnesium metal. If we did lithium metal instead, what happens is we do a halogen metal exchange, and where we used to have the halogen, we now have a lithium. Now, if we consider the nature of this methyl group, this carbon, what kind of charge do you associate with a lithium? What's the oxidation state of a lithium? +1. So we could say partial +1 if you like, which again makes this carbon partial -1. So this is another example of a nucleophile. All organometallic reagents are going to be nucleophilic. Unfortunately, he doesn't have a cool name like the Grignard. This is just called an organolithium. An organolithium reagent, and has this general formula of some kind of carbon group with a lithium attached. We call those organolithiums. And what's great about these Grignard reagents or organolithium reagents and organometallics in general is this R group that you're having the metal attached. The R can be almost anything you can imagine. It can be an alkyl group, just like we saw here. Here we have a methyl. Here we have a carbon chain. So you could attach a metal to a random sp3 hybridized carbon group. But you can also have aryl Grignards or aryl lithiums, phenyllithium for example. So you can have a metal attached to an sp2 hybridized carbon. Or vinyl, you could have it part of a double bond. So huge variety in the types of carbon groups that can be attached to a metal and therefore be nucleophilic. So when it comes to synthesis, these organometallic reagents are really going to open up the door for us for making all sorts of interesting and new molecules. So let's think about the reactions that an organometallic might undergo. We just learned how to make them. How do they behave? What can they do? Well, one reaction that they have is that they're extremely strong bases. In other words, they can be protonated. Okay, if we have this magnesium chloride on this carbon chain and we react it with an alcohol like this, we just learned how alcohols can be acidic. This is an acid. This is a very strong base. And so we're going to get a proton transfer reaction to take place. Now, one way we can show this reacting, sometimes we just see the arrow coming from this carbon-metal bond, okay? But I think an easier way to do the mechanisms for these is wherever you had the metal attached, you treat that carbon as if it has a lone pair and a negative charge. Okay, now it doesn't really. It's not an ionic species, okay? But that's a very helpful way to view it. It's a very helpful way to show mechanisms. And so what we do is we'll just put quotes around this species saying, well, we don't really have this, but it acts just like it. So the quotes let us get away with that. And now we can see this base clearly has a lone pair and a negative charge like other bases do, and we can clearly see how we can do that proton transfer. The base grabs the proton, leaves the electrons behind, and so the product we get is my cyclopentyl group is now has been protonated. We have a proton in that position. We also made some methoxide here. We deprotonated the alcohol and we protonated the Grignard in this case. Okay, what is the salt here? This is going to be like an MgBr salt of the alkoxide. Now, typically this is a side reaction. This is not a valuable reaction. This is something we're going to try and avoid. What's very important to know is that Grignards will react with water. Just like it'll react with alcohol, has an acidic proton. Water certainly has an acidic proton. So we must use very dry glassware, dry solvents. We can flame dry our glassware to get rid of any residual moisture that might be attached to it. We'll store our glassware in an oven to keep it super dry, and then set up the reaction under argon or nitrogen, some in our atmosphere, so that it's nice and dry. Our solvents, we'll put some drying agents, or we'll freshly distill it so it's super dry. Okay, any bit of moisture in our reaction mixture or in our atmosphere has the potential of quenching our Grignard reaction, of reacting with our Grignard reagent and destroying it. Okay, so we're going to be very careful to do this kind of reaction in the appropriate conditions. Okay, of course, when it comes to a solvent that we're using, we can't use a protic solvent like water or an alcohol because the Grignard can't exist in those conditions. Instead, we need to use aprotic solvents, okay, things like ethers, diethyl ether, THF stands for tetrahydrofuran, has this formula. Okay, so some kind of ether is going to be used. And again, we should kind of get used to these names of solvents because it's going to be very commonly part of your reaction conditions is listing the solvent, so you don't want to worry too much about that when you see it or try and use it somehow as a reagent. It's just a solvent, and all of our reactions have solvents associated with them. And there's one way that we can make this a useful reaction, and that's if we wanted to introduce a hydrogen into our structure, or maybe even a deuterium. Deuterium is, which is what D stands for, is an isotope of hydrogen that has a neutron in here, so it's H2, and it's so commonly used, instead of calling it H2, we usually just use the letter D to represent deuterium. And sometimes we want to include isotopic labels in a structure. This would be a way that we could do something like that. For example, if we had a bromine here in our benzene ring, and we reacted this with magnesium, that would insert a magnesium and turn this Br group into an MgBr group. And then what would happen if we reacted this with D2O, deuterated water, instead of H2O? Well, we would expect that phenyl minus to protonate, deuterate in this case, at a D+, and therefore you could get a deuterium installed in your structure. So this is actually, it can be a useful reaction, but by and large the reaction with alcohols and water just kind of help us, guide us in our experimental conditions to make sure we avoid those so that the side reactions don't happen. Okay, where we're typically going to be using our organometallic reagents like a Grignard is as a strong nucleophile. This is where it's most useful, which means it reacts with an electrophile like a carbonyl. Not alkyl halides. We've seen those as electrophiles before, but these do not react with Grignards. Okay, we'll see an example of that. So for example, let's say we had methyl lithium and cyclohexanone with some THF. What if we mixed all those together? Okay, the methyl lithium, remember this is like having a methyl minus. The lithium gives us a plus charge, so that means it's like we have a methyl minus, definitely a nucleophile. I'm going to put that in quotes to remind myself it's not really ionic, but that's it reacts kind of like that. And is the carbonyl in this ketone, is the carbonyl an electrophile? Absolutely. This carbonyl carbon, remember, is always partially positive. We'll be seeing dozens of cases of that when we study carbonyls. And so what happens when you mix these two? This is going to attack the carbonyl and break the pi bond. I kind of moved that up a little hard. Can attack the carbonyl carbon and break the pi bond. Doesn't matter if you show it coming from the right or left. But it's going to give me an O minus where the carbonyl used to be. And then after workup, step 2 is workup. I'm going to protonate that O minus. And I just synthesized what kind of functional group I just made, an alcohol. Okay, so this would be a nice way to synthesize an alcohol. Furthermore, notice what we just did here. Because we had a carbon nucleophile and a carbon electrophile, we just made a new carbon-carbon bond. So again, that's kind of unique in organic chemistry. That's a pretty special reaction to study. So that's extremely useful. Grignards are extremely useful, or organolithiums, for making alcohols and creating new carbon chains in the process. Okay, let's take a look at this example. We have methyl bromide. Methyl bromide is definitely an electrophile because we have a carbon bearing a leaving group. Phenyl magnesium bromide, what does that mean? We have phenyl minus. We put that in quotes, so it's just like having a phenyl ring with a lone pair and a negative charge on one of the carbons, so kind of a strange looking species, but that's how it behaves. Okay, and what would be very tempting here, what makes sense is, well, we can have this attack the carbon and kick off the leaving group. Very tempting to do. Okay, however, it does not happen. Okay, and that's just an exception that we really need to get used to seeing, is that Grignards do not react with an alkyl halide. Grignards, And when I say Grignard, I mean Grignard or organolithium. They're pretty much going to be used interchangeably for most of our reactions. Grignards don't do SN2s. They don't do SN2 mechanisms. They're not there to react with an alkyl halide. Remember, how did you make this Grignard? You started with a halide. So we use alkyl halides or any kind of halide to prepare a Grignard. That wouldn't work at all if the Grignard, as it was being formed, started to react with the starting material. Okay, so they are compatible with each other. Grignards and organolithiums will not react with alkyl halides. We're just going to have to try and keep that straight because it's really kind of a reaction that is a logical one, and one, in fact, that a lot of students make mistakes for in doing so, but we just need to remember that this is the one reaction that Grignards don't do. So they're going to react with carbonyls, but not with alkyl halides. The other nucleophile we'll take a look at for synthesizing alcohols is the hydride nucleophile. Okay, hydride again means we have an H with a lone pair and a negative charge. Okay, typically for the reagents that we're going to be seeing, especially when it's being nucleophilic, again, we're going to put that in quotes because these are not ionic species. The hydrogen minus is not floating around on its own. It's always going to be coordinated to a metal. We're going to either use lithium aluminum hydride or sodium borohydride. You can see how similar these species are. Okay, and that aluminum is going to take one of the hydrogens and deliver it, or the boron is going to deliver a hydrogen, but it's going to react as if it was an H minus. So let's see an example. If we start with a ketone or an aldehyde, if we start with a carbonyl and we react with lithium aluminum hydride, this actually is often abbreviated LAH for lithium aluminum hydride. So in step one, if we react this with LAH, that gives us a source of H minus. This is one of those cases where really saying the name of the reagent and thinking about the name of the reagent is going to help us predict the product, because the name of the reactive species is part of the name. It's lithium aluminum hydride. Right there we see that we have H minus. That means we have a nucleophile. We need to look around for electrophile. Okay, and this carbonyl will be our electrophile, so we attack the carbon and break the pi bond. Carbonyls do the same thing all the time. And we now have a hydrogen attached and an O minus. So just like with the Grignard, we're going to follow this up with a reaction to get rid of the O minus. We're going to do step 2 is some kind of aqueous workup. So step 2, we protonate. And our product is an alcohol. Now this is described as a reduction reaction. We could describe this as a hydride reduction because we increase the number of CH bonds while decreasing the number of CO bonds. Okay, so ketones and aldehydes can be reduced with a hydride reagent, either lithium aluminum hydride or sodium borohydride, to give, as a result, an alcohol product. Let's see a few examples of this. Now we just saw one with lithium aluminum hydride. With LAH, we need a 2-step process. First we react with LAH, and then we react with H3O+. We do a workup. Okay, NABH4 is less reactive. This is less reactive than LAH. So we don't need to do a stepwise approach. We can actually use as our solvent a protic solvent. So the NABH4 is going to be donating our H minus, and the methanol here is going to be donating the H plus at the end. It's going to be available for kind of like our, instead of a separate workup step, it's going to be our final protonation step. Okay, so what happens? Same thing as LAH. We attack the carbonyl. Let's see if we could just draw a product. We have our nucleophile added to the carbonyl carbon. And what used to be the carbonyl is now an OH. So we have those that same pattern each time, whether it's a Grignard or a hydride. We add the hydrogen, we add the nucleophile to the carbonyl, and our carbonyl is now an OH. Okay, let's try one more. How about if we took this this ketone and we react it with hydride and alcohol, we expect to reduce the carbonyl from a ketone to an alcohol. Okay, we could do the mechanism for that. And what happens with this alcohol then if we treat it with H2SO4 and heat? We saw that as a dehydration reaction. This is a way to remove water from an alcohol and form an alkene, form a carbon-carbon double bond. Let's think about the regiochemistry. Is there more than one alkene that's possible? Where would the best one be? We have our leaving group here, but our carbocation, remember, can go anywhere it wants because those can rearrange. So what would be the best location of the double bond in our final product? I think we're going to want to go here so that the double bond is now conjugated with the double bonds that are already here in the benzene ring. So this is the major product. And it's more stable than having the double bond in this position, in the vertical position, more stable because it is conjugated with the existing pi bonds. That means it has resonance. We can have delocalization of these pi electrons. We have p orbital, p orbital, p orbital, p orbital. We have all these p orbitals are linked, and so we can have delocalization and resonance of that alkene. So that's going to be a more stable case because it's conjugated. Remember Zaitsev's rule? Remember Zaitsev's rule tells us that the more stable alkene is always going to be our major alkene. Let's look at a few more examples. How about if we wanted to do this transformation? Here we have a 1-carbon chain, and now we have my carbonyl is now an OH, and we have a new carbon here. So let's draw this in as a methyl group, as a CH3, expand our line drawing. It looks like this is a new group that's here, that's been added. If we wanted to react with this carbonyl carbon, we know that this is electrophilic. This is partially positive, so it's electrophilic. So what we need to react with that carbon is we need a methyl that is a nucleophile. How can we make a methyl be nucleophilic? Well, I think all we need to do, if we had a lone pair and a negative charge, that would make it nucleophilic. How do we get to that reactivity in that species? Well, that's exactly what a Grignard reagent does. If we have CH3MgBr, that is nucleophilic, and that would react with the carbonyl. We would do that as step 1, and as step 2, after doing the Grignard, we would need some kind of aqueous workup, H3O+, for example, and that would protonate the O- to give an alcohol product. So more than doing just a simple reduction of the carbonyl, we also added in a new carbon group. So this is how we could use our Grignard reagent. Okay, here's another example with an organometallic. Where does this alkylithium come from? How do we make an organometallic? Well, when we make this, right, if we ask what starting materials do we need, right, we're seeing the reaction conditions here. We've added in lithium metal. What did that lithium metal react with? Well, what did we need in that position? We needed a halogen of some kind. So we need an Rx to go to an alkyl lithium or a Grignard reagent too. So you can pick any halide you want, bromide, chloride, iodide. They would all do a good example. Okay, so the Grignard and the hydride reagents are new reactions, reacting with the carbonyl. Those are new reagents that are very useful in forming the alcohol functional group, and so that's useful. That's a new strategy for forming synthesizing alcohols, and we can add that to our list of other reagents where we're doing more of a functional group interconversion on going maybe from an alkyl halide to an alcohol, or from an alkene to an alcohol, by doing those sorts of transformations as well. The next part of the alcohol unit is going to look at reactions of alcohols. Once we have an OH on a structure, what manipulations can we do to it? What transformations can it undergo?